Okay, so far in chapter 25, when describing currents, essentially you're seeing it on a macroscopic scale. That is describing things in terms of circuit elements and resistors and so on and so forth. So for the remainder of the chapter, now we kind of start to focus in on what is happening microscopically. First of all, a little bit of some of the other further details associated with resistance. Okay, so let's say that I have here a wire, which I'm just going to draw out as a cylinder, like so. It has a length L associated with it, and it has a cross-sectional area A associated with it. Basically, the total amount of resistance R associated with this section of wire basically depends upon two things. So think of it in the following manner. The longer the wire, it's like the longer your pinball machine. So then therefore, the longer your pinball machine, the more bumpers you have in that pinball machine. This then means that the resistance increases with length. So the more wire that you have, the more energy you lose as heat. Just think of it that way. So then therefore, the resistance itself is directly proportional to the length for that reason. It's also inversely proportional to the area. So the wider the area of the cylinder, the easier it is for the current to flow. Think of this by analogy in terms of a water current. So the wider the river, the easier it is for the water current to flow. Same idea here. So if you increase the area, then therefore the resistance goes down. This means that the resistance and the area are inversely proportional to each other. Like so. Okay? Combine the two expressions together, and when you do, you end up with this. So what is then therefore the proportionality? Proportionality is a property of the metal itself. It's what's referred to as the resistivity. The resistivity is essentially a complicated function of exactly what happens when electrons are interacting with the metal that makes up the wire itself. So it's a slightly different value than therefore for different elements, copper, aluminum, tungsten, and so on and so forth. Okay, the symbol that is used to describe resistivity is referred to as the Greek letter rho. So we've seen rho in terms of density, for example. That's not the case here. In this case, we're describing this property associated with the metal itself, referred to as resistivity. So the resistivity is written as rho. And it's a property of the metal. And it's basically a complicated function of what happens when the electrons interact with the atoms that make up that metal. What happens when electrons interact with the atoms that make up the metal. So therefore, we write the expression for resistance in the following way. Resistance is equal to the resistivity rho multiplied by the length L and then divided by the area A. Okay, the units associated with the resistivity rho, it comes directly from this expression. So we have ohms here, and then we have meters squared, and then we have meters. So if you cross multiply everything to the right-hand side of the expression to get the units for resistivity, you end up with ohm meters. Ohm meters, like so. Okay, should you encounter the resistivity on the actual AP exam, it would literally be nothing more than a plug and chug type of problem. And by the way, while I'm thinking about it, we also define the inverse of the resistivity as well. The inverse of the resistivity is referred to as the conductivity. And the conductivity symbol that we use is another sigma. Like so. So 1 over the resistivity is referred to sometimes as the conductivity, but the one to really remember is the resistivity itself and this expression. Okay, so I have one lecture example associated with resistivity, so go ahead and copy that problem down into your notes. As I said, it's really nothing more than a plug and chug type of calculation. Let me go ahead and refer to it here. Okay, I'm going to do some erasing. Okay, and then we have our expression. Okay, so compare the resistance of the following. We have two types of wires here. Okay, first of all, we have 10 meters of aluminum wire with a 2 millimeter diameter, and then 25 meters of copper wire with a 2.5 millimeter diameter. The resistivities of aluminum and copper are given to us as these values respectively, 2.65 and 1.68 times 10 to the minus 8 ohm meters. You're always going to be given the resistivity of the metals in a problem such as this, and once again, it's literally nothing more than plug and chug. All right, so let's see what happens first of all with the aluminum. All right, so for the aluminum, the length L is given to us as 10 meters. Okay, and then right here is the radius R associated with this cylinder. If it's 2 millimeters in diameter, this then means the radius is 1 millimeter. So this is 1 times 10 to the minus 3 meters. And the area itself is just going to be a pi r squared type of calculation, the area of a circle. Okay, the resistivity of the aluminum is the 2.65 times 10 to the minus 8. So I'll call this rho AL, like so. So 2.65 times 10 to the minus 8 meters. And now basically you just plug everything in, and it's nothing more than that. All right, so the resistance is going to be rho L over pi r squared. And now we just calculate this out. Nothing more than that. All right, so 2.65 times 10 to the minus 8, and then multiplied by the length L, 10 meters, and then divide by pi r squared. So pi times 1 times 10 to the minus 3 squared. And I end up with a really small value. This is one of the reasons why we use these metals in wires, because they have a small overall resistance. In this case, it's 0.084 ohms. Like so. Now let's compare that to a copper wire. Okay, so for the copper, we're given a length L here in this case of 25 meters. Okay, and then 2.5 millimeters in diameter. This then means that the radius R is half of that. That's 1.25 millimeters. So that's 1.25 times 10 to the minus 3 meters. Of course, everything has to be in the correct units. And then we're given the resistivity of copper here. I'll call it rho Cu. That's equal to 1.68 times 10 to the minus 8 meters. And then once again, we just calculate. So R, the resistance, is rho L over pi r squared. All right, so now we've got the resistivity here of copper, 1.68 times 10 to the minus 8. Multiply that by the length of 25 meters, and then divide by pi r squared. So pi times 1.25 times 10 to the minus 3 squared quantity. And this comes out to be almost similar, or pretty similar rather, to this value here. It's about, here we go, 0.086 ohms. Like so. So this illustrates the reasons as to why we use these metals, for example, in electrical circuits, because their resistances ultimately are pretty low, even when we make really long wires. Okay. All right, so that concludes this short lecture. Or this part of it anyway.